Hi, today we're solving problem 39. If P is the perimeter of a right-angled triangle with integral side lengths ABC, there are exactly 3 solutions for P equals 120. So here we have 3 different variations in right triangles with perimeter 120 and integral side lengths. For which value P less than equal to 1000 is the number of solutions maximized? The way we're going to solve this is find an equation that, given the perimeter of a triangle and one of its leg lengths, find the other leg. So I'm going to go over and switch over into IntelliJ. So I'm actually just going to do this in a comment. So let's start by putting the Pythagorean equation up here. A squared plus b squared equals c squared. And we also know that a plus b plus c equals p. So we're given the perimeter p plus c equals p. Now, what can we do with this? Well, what I'm going to do here is I'm going to rewrite this equation in terms of c. So c is equal to p minus a plus b. And now I can plug this into this formula. So I can replace c squared with this value squared. So a squared plus b squared is equal to p minus a plus b squared. And now we can expand this. So we get a squared plus b squared equals, here we do. And if this is our first term and this is our second term, we can just expand this. So we get p squared minus 2 times p times a plus b plus, and now we get a plus b squared, which is a squared plus 2ab plus b squared. Now we can cancel some stuff, so we can get rid of a squared plus b squared here and get rid of a squared and b squared here. And I'm actually going to move this over to the other side. Okay, so now we have 2p times a plus b is equal to p squared plus 2ab. Now I'm going to change this formula so that it's in terms of b. So we calculate b in terms of a, and this will allow us to get the other leg length based on one leg length. So I'm going to do, I'm going to expand this first. So we get 2pa plus 2pb equals to p squared plus 2ab. Now I'm going to move all of the terms that involve b to one side. So then I get 2b times p minus a. So that's this term minus this term. So I'm moving everything to the left side. And this is going to equal to p squared minus 2pa. And what we're working here with, since we're looking for integral side lengths, this is actually what's called a diophantine equation, in which the variables are going to be integers. And one thing that's useful to do when you're working with diophantine equations, especially in the context of an algorithmic problem, is dividing one side by the other. So what I'm actually going to do is I'm going to take this everything other than the b and divide the other side by that. So then I'm just going to be left with b is equal to p squared minus 2pa divided by 2 times p minus a. And so here now we have b in terms of a, and we can easily test this to see if it produces an integral result by calculating the numerator and the denominator and doing a modulo on this. So that's it. So now we have a quick way to test out values for this diophantine equation. So the way we're going to solve this problem is we know our perimeter, we know what possible values for A we might have, and based on those values, we can calculate all possible values of B that are integers, and that gives us the number of possible cases. And then we're just going to iterate over all perimeters and calculate how many cases we have. So I'm going to do def triangle cases for a perimeter of type int. What I'm going to do is first I'm going to iterate over all possible values of A. Now A is a leg length, and we know that the hypotenuse is at least the length of the leg. So we don't even need to go all the way to the perimeter to test values for A. We just go from 1 to the perimeter divided by 2. Now, for each of these, we're going to count the ones. So this is A. Given A, we're going to calculate the numerator and denominator of this. So I'm going to do val B numerator, and that's going to be perimeter times perimeter minus 2 times the perimeter times A, and the denominator is going to be our perimeter. Actually, we should start with 2 probably. 2 times our perimeter minus A. So now we have our numerator and our denominator. And the first thing we want to check is that our numerator is divisible by our denominator. Our denominator. Yeah, our numerator is divisible by the denominator. I'm getting confused here a little bit with the fractions, because this numerator divided by denominator should give us an integer. So first we want to check that b num mod b den is equal to 0. So this is checking that when we take the numerator and divide it by the denominator, there's no remainder, and that tells us that this is producing an integer, not a fraction. And we want to check this, and I can probably get rid of those parentheses here actually. We want to check that B is less than A, because we want to mandate an ordering between A and B, because normally with the right triangle you can just swap the values of B and A and you'll get another right triangle. But we don't want to double count these, so we can just do B numerator divided by B denominator is less than or equal to A. And that gives us the number of cases given our perimeter. Now we can println. All we need to do is go from 1 to 1000. This is all of the cases for our perimeter. I'm going to filter, or actually, I need to find the value of P for which the number of solutions is maximized. So I can actually do max by. So max by will give us a value that produces a maximum result, and that result is calculated via a function that you pass to max by. So max would just give you the maximum value. Max by gives you the maximum element that produces the element that produces the maximum value. So here we're going to put in triangle cases. We can just pass this, and now we can run. So I run here, and we get our answer, 840. So that's it for problem number 39. I'll see you next time when we solve problem 40.